So I just want to review inductors, conductors. I just have a short simulation here to remind you what we have learned in a nutshell. If you have an equation, I'm available after the class. Before the class, it's very hard to make it at 9:30. 10 a.m. was much better. Come on. So slow. So remember, if you rub like a balloon and hair, or rubber and fur, it's going to be the rubber, it's going to be the balloon that will take the electrons. Okay, because rubber likes electrons more than fur, for example. So you always have this conceptual question for the pop quiz or the assignment. So in that case, you see, so you see this is an insulator. That's why the electron have been moved, transferred there, because you have done work. Okay, so the electrons were transferred there, but they cannot move. Okay, they cannot spread out because it's not a conductor. If it was a conductor, the electron would have gone through your body into the ground, but they can't. Even though you have transferred electron from the fur to the rod, the electrons here are blue. And then here, what you see here, it's called polarization, because this is not a conductor, it's an insulator. So electrons are not really moving. They can't move in an insulator, but you have something called polarization. Okay, so it's going to be important to understand that when we get to dielectrics. So if I take this, okay, so what's happening inside is that the molecules here get polarized. So you have a plus and a minus, a plus and a minus, and a plus and a minus, but the electron cannot move. And then the molecule inside are also polarized. So plus, minus, and then you have a plus and a minus, and then you have a plus and a minus. Okay, so the molecule will change shape, but the electrons cannot move. So at the end here, okay, you're going to have minus at the end, and so that's going to be minus here, and that's going to be plus. But electrons cannot move, okay, because it's an insulator. So it's called polarization, and if you go to electrical engineering, you learn about, for example, dielectrics. Okay, so if you have something like a capacitor, so remember, capacitor is like a defibrillator. So you have two electrodes, you connect that to a power supply, that will be negatively charged, positively charged. In between them, to enhance the capacity of the capacitor, meaning you want to store more charge, in between them, you have something called a dielectrics. So we will learn more about it. My point is that material here is insulator, and the molecules in between get polarized. Okay, so it's an important concept if you go to electrical engineering. Okay, now if I take a glass rod, so usually the glass rod, you're going to rub it with silk. Silk love electrons. Okay, so you are doing work, you are taking electrons from the glass rod to the silk. You see, now it's missing some electrons, and again, you get polarization, except here it's going to be minus, and here it's going to be plus. Okay? And I sent you like a link in announcement and a free textbook. It's very good. It's a very good free textbook. So at least you need to open your textbook. You have to learn on your own because we don't have enough time together. We don't have recitation. I have no TA. They refuse to commute from MMC to BBC. So I have to grade 100 students and there is no TA to help me out. So this is a conductor. So because it's a conductor, now electrons are free to move and they will move away as far as they can, okay, from each other. And that was in the 19th century, that was a way to measure charges, relative charges, right? So more charges, the angle will be larger. And if you touch it, then it's going to stay charged, right? The electron will stay there, okay? It can hold charges. That will be also called a capacitor, because if you have minus somewhere, and usually this is connected to the ground, so there you're going to have plus, okay, minus and plus. So it's also called a capacitor. And how many charges you can hold depends on the geometry. So you're going to see you have computer equations to find how many charges you can hold depending on the geometry. Now, if you ground, I don't know how you can ground it, but if you ground, it will come back, okay? You can do the opposite here. So now it's negatively charged, positively charged, okay? Boom. And now it's the opposite. Okay, so if you have an equation, don't hesitate, because sometimes professors take it for granted that you all know the stuff. And unfortunately, it's not the case. Okay, so then we learned about Coulombs law. And I had a great website, but I lost it. Here, it's another free, lots of free stuff. So positive and positive repel, negative and negative repel, positive and negative attract. But it's, so first of all, Newton's third law, you cannot pull without being pulled, and you cannot pull more than you are being pulling, which means the force is always the same. It's inversely proportional to the distance square, meaning if you multiply the distance by 2, the force is divided by 4. And it's a very nice website here, because you see this force here is 1/4 that one. If you multiply your distance by 3, so you take this 3 times, the force will be divided by 9. Okay, so that little thing fits 9 times into this one. And then it has to be proportional to the product of the charges. Makes sense, because nature doesn't like favoritism, right? Why would you favorite this one and not that one? So it depends on the charges, obviously, and you multiply. And then you just need a constant. You need a constant, the electric constant. That electric constant is really big, because electric forces is what is holding us together, okay? That's the glue that glue all the molecules inside us together. And gravity is very weak. That's why the gravitational constant for gravity is going to be 10 to the negative 11. Otherwise, I will not be able to stand up. I will be crawling on the floor, which will be not very nice. So this is Coulomb's law. And the constant sometimes, for historical reason, yeah, it's written as 1 over, open the parenthesis, 4 pi epsilon 0. And this is called the permittivity of vacuum. And it's in your equation sheet, okay? So this is just a review. And then I told you to review vectors. I've said at least 3 or 4 times, I don't know. Okay, so let's do this one together. It should not take too long. You can help each other. So I will show you the methodology. So they want to find the force on Q1. So that means your system is Q1. Okay, so you're going to take this one in a bag. So that's the one you want to look at. And then you're going to look at all the forces applied to Q1. So you circle out Q1 and you focus on Q1. So you isolate Q1. Okay, you take it away from the system. And you see here plus minus, so it's going to be attracted here and attracted there. Do you agree? So you always start by drawing. Once you are done drawing, we are adding vectors. So the first thing is to do is to find just the magnitude. We're going to find the magnitude, and then we're going to deal with X component and Y component. And again, in Dropbox, you have tutorials about vectors, and you need to review that. I cannot do it for you. You have to do work on your own. Yes, yes, yes. And if you don't see the red dot here, that means I forget to record. You don't want me to forget. So this is 1D. So 1D is easy. So first thing you decide which way is plus, which way is minus, right? So the first thing you need to have a frame of reference that will be the x-axis. So the second thing you want to do is to find just the magnitude, okay? Just the magnitude, how strong. And then you apply Coulombs law. Then you apply Coulombs law, okay? So it's going to be the constant and then the charge of one okay, the charge of one, so Q1, so this is 1 and 3, so it will be 3 times 10 to the negative 6, and then you have 7 times 10 to the negative 6, okay? I don't care about negative because I found only, I'm looking at the magnitude only, and then the distance square, so 0.5 square. Okay, so just the magnitude, and then 1 and 2. So it doesn't matter if you put 1, 2 or 2, 1 because the same force. And that will be 9 times 10 to the 9 and the charge and the charge. And then you take your TI and you have to do it in one shot. Okay? And don't stare. You have to do it. Do you get that? So only the magnitude for now, right? So take your TI and you open the parentheses, you do 9E9, close the parentheses, open the parentheses, 3E negative 6, close the parentheses, and then open the parentheses, 7E negative 6, close the parentheses, enter, divided by 0.15 squared, enter. So you don't need multiply, and for the base 10, you just put second comma if you have a TI. Okay, so what did you get? 8.4. Very good, 8.4, right? Tell me your name if you participate. And then 1 and 2, it's going to be 2.7 Newton. Do you agree? And again, this is just magnitude. But now we have to remember that it's a vector, okay? We are adding vector. So the net force will be the vector 1, 3 plus the vector 1, 2 here. So 1, 3 is to the right, so it's going to be positive. So I'm projecting along the x-axis. This one is to the left, so it's going to be minus 2.7. Okay, that will be 5.7 Newton, and it's positive. So I can make a new drawing, Q1. Okay, so that's my bag, what I'm looking at, and the net force is positive. So it's going to be this way. And then if it is free to move, it's going to accelerate. Okay, the acceleration will be the net force divided by the mass. So we can use a little bit of physics 1. Is that clear? And this comes from an algebra-based book. So you really have to open the book Okay. So it says here, so that's the textbook recommended, which is University Physics. It doesn't matter which edition you get, it will be the same solve problem. If you buy it for the school, you have videos, you have tutorial. Otherwise, just get the older edition, and that means you should do 21.2, 21.3. So we are doing chapter 21. Is that clear? And then I told you to review vectors. So how do we add vectors? You can do it geometrically, using geometry. So you can do tail to head, or you can use a parallelogram. So I'm not going to teach you that again because we did it last semester. Or for the components, you add the components, right? So the x component of the sum equals the sum of individual x component, and then you add the y component, and then you have the x component, the y component, you can find the magnitude and the direction. Okay, so remember from last semester. So how do we apply that here? So conceptually, I'm just going to show you the methodology. So here we have what it's called a dipole. Why is it called a dipole? Because let's say you have Q1 and Q2 and the charge is the same. And you want to find the net force applied on Q3. So then that means you're going to focus on this one. That will be my focus, right? You have your special glasses, physics glasses here. You look at this one. So this one is going to be pushed by that one because this is positive, and it's going to be attracted by that one. If the charges are the same, this force will be larger because the distance is smaller. So if I want just to do it geometrically, okay, I can use the parallelogram method. So I can make like a parallelogram. This is a parallelogram here. Okay, and the net force will be somewhere there. So that way, you see, it's a way to check your computation. Because you see the net force, if it's in the second quarter, that means the x component should be negative and the y component should be positive. Okay, so that way you can check your computation. And again, you have very good tutorial in my Dropbox, so I hope you did that already. Is that clear? So it's a vector sum, and the only way we can do that, we can say the x component of the net force is the x component of 1, 3, right? Plus the x component of 2, 3. And then you have the y component, which is the y component of 1, 3, and the y component of 2, 3. So then you have the x component and the y component. So x component, y component. You use Pythagorean theorem to find the magnitude, and then you can find the direction using tangent. Is that clear? So just a review from last semester. Again, you are supposed to go over the tutorials in Dropbox, because or chapter 1 of your textbook, because I cannot teach you again physics 1, but that's the idea, just a review here. Okay, are you with me? Okay, so let's take an example. Try to do this one. So you can help each other. The first thing to do is to isolate what you are interested in. So you isolate Q1 and you say, okay, what's going on with it, right? What are the forces applied to Q1? And then you're going to find the magnitude of the forces using Coulombs law. Only when we have found the magnitude, then we take care of the x component and y component using trigonometry. Okay, so here you have the steps. So I'm lost here. So can you do it? Good morning. So help each other, talk to each other, blah blah blah. Go, go, go. Let's go. Let's go. Let's go. Okay, so again, you need to open your textbook. Whatever textbook, it's the same physics since the 19th century. So it doesn't matter which textbook you get. University physics is a very nice textbook, but you need to get the textbook, right? So we are focusing on this one. So you isolate this one. What's going on? Plus, minus, attract. So they're gonna like each other. Yeah, I like you. And you have a plus and a minus. Oh, I like you too. Okay. F12. Agree? So that way you know where you are going. We are supposed to find a net force in the first quadrant. Looks like it's a first quadrant. Let's see. Okay, first step. Step number 1, you only find the magnitude. Only the magnitude, okay? With your TI, you do that in one shot. 9e9, and then 5, 10 to the negative 6. Open the parentheses. Don't put a times. With the TI, you can do that in one shot. And then 4e. E is second comma. Okay, enter, and then you divide, open the parentheses, and then 0.1 square. Okay, so we get take care of the magnitude. Yeah, do it as we do it here, so you won't have to do it at home again. More you do here, less you have to do at home. One shot. Good morning. If you want me to do it with a TI just to show you I can do, and then 1, 2, same thing, one shot. And then 6 times 10 to the negative 6, and then you have 4 times 10 to the negative 6, and then you have the distance square, which is 0.15 square. And you get, yeah, what's your name? Oh, yeah, you moved. Yes, exactly. 9.6 Newton. Are you with me? Okay, so that's just the magnitude. And then we need to take care of the components. So for 1, 3, it's just X component. We don't have to worry about it. And then you see here F12, we have to be careful to make sure the component is it positive or negative. You see, you go from the tail to the head. So you go this way, that will be the X component, and you go up, that will be the Y component. X component is positive, Y component is positive. Okay, and we have to be careful the cosine. In that case, it will be cosine. So, okay, so the X component of the net force will be the X component here, which is just 18. That X component here is positive, so it's going to be 9.6, and that will be a cosine 73. Okay, like we did for physics 1. Hopefully you saved your USB physics 1. And then the Y component, okay, you have 0. Okay, there is no Y component. And then this one is the magnitude, so 9.6 sine 73. Okay, one shot with a TI. Agree? Okay, so that will be 21 Newton, and that will be 9 Newtons. Did you get that? Okay, and then to make sure to get it right, we have to draw again. So when you find the net, a vector sum, you have to draw again the X, Y coordinate system to make sure to use the tangent the right way. And you try to do it on scale. So this is about 10. Okay, so I'm going to do here, that will be the X component here, X component, and that will be, the X component is 21. So It's about here, right? This is 21 and this is 9. So that will be the tail of your vector, okay? So that will be a vector here. That will be the net force. See, it has a x component and it has a y component. It's a vector. A vector has a tail. The tail is always attached to the origin, just to review. So that way, you are, because you know, multiple choices, you will have always the choice between here and there. So you want to use tangent, but wisely. Because one of the multiple choice will think what mistake you're gonna do. So it will be arc tan opposite is 9/21. Is that clear? So this is a review. I just wanted to show you the methodology. And you again, you have to open your textbook. You have to hide the solution, at least of the solved problem. So the trick is when you start a new chapter in chemistry or whatever, you start by looking at all the pictures and what the picture says underneath. So you get an idea of what's going on. And you ask yourself questions, right? And then you browse through the chapter and you do the solved problem and then you can read deeper. It's not easy to study. There is a way to do it. So anyway, so the magnitude is, we don't know the magnitude because we have to do Pythagorean theorem, which is 21 square plus 9 square. So that will be the magnitude. And then at 25 degrees above the positive x-axis, and the unit is Newton. Okay, so how much? 23. I think it's 23 of what Newton? Which way? 23 degrees above the positive x-axis. So if it doesn't say anything, you suppose that it's a positive x-axis. Question? Okay. So that comes from algebra-based book. Okay. And it says 21.4, so you should do 21.4. Lot of application in electrostatics, lots in technology and in the human body. Everything is electrical in nature. Everything is about charges, right? So this is, for example, this is an application. So these little beads here, do you think they are negatively charged or positively charged? According to the picture. Negative, right? Because plus and minus attract. So they're going to be repelled here. Negative and negative will be repelled, and you're going to see white, and here you're going to see blue. Other application, we already talked about that. You have a drum, you have a spark, like a discharge, corona discharge. That's going to be positively charged. This is made of semiconductor. And then here with semiconductor, you know, you can kick charges, right, with light. That's what you are doing here. The light kick out all those charges and you are left with a positive 3. That will be the shadow. And that's going to be stick to the negatively charged ink powder. It's a powder. That's why you put your finger. It's all sticky, and that's how it works. Copy machine. Now, in many examples in the human body, DNA, you have hydrogen bonds because hydrogen is kindly giving away its electron. So nitrogen is taking the electron. This is positive. Oxygen is always oxidative stress, right? That means it takes electron wherever it can. So you have a bond here between the minus and the plus. Okay, nitrogen and oxygen, and they love electrons. So that's an application. That's how it works, okay? Everything, DNA, RNA, all those stuff has to do with electric forces, an electric field. Lot of application. I told you about Ernest Hemingway, didn't I? I think I did, right? So lots of applications. Okay, let's review vector field. That's I introduced that in physics 1. A vector field is a mathematical function such that every point in space you can associate a vector, a magnitude, how much, unit of what, and a direction which way. So in that case, that will be the velocity of the wind. Okay, so how fast and then which way it's blowing, and what's the unit? I don't know. Here it's meter per second. So you can represent a vector by an arrow, but then it gets very messy. So you have a different way to do it. Okay. To represent a vector field, we can use streamlines. So when the lines are packed together, that means larger vectors, so larger wind. If they are the density is less, that will be weaker vectors, weaker wind. And you can do that in 3D. Okay, this is just 2D. Are you with me? Right, so you can go on YouTube, you can watch this video just to give you an idea. So for example, last year we learned that the Earth is generating an aura, okay, around it, and it's called a gravitational field, and we can represent that with a vector field. So every point in space will be associated with a gravitational field, G. It's a vector. It can be stronger close to the Earth and weaker as you move away. It's an inverse square law. Okay, so here, at that distance here, the field is 9.8. If you multiply the distance by 2, so twice the radius, the field will be divided by 4. 3 times the radius, the field will be divided by 9. It's attractive because gravity is always attracting. If you place a mass inside that field, okay, like the moon is going to feel that there is a field, and it will react to it with a force at a distance. Okay, so we're going to review that. Okay, so gravitational field. If you do fluid mechanics, you do that with fluid. Okay, the water can flow, or the wind, you can see every space. And we're going to do that with electric field, right? A charge, we're going to do that right now, like in 2 seconds. A charge, like a positive charge or a negative charge, will also create an aura that is called the electric field. And if you place a charge in that aura, it will respond to it with an electric force. So anyway, as it gets complicated, right? So here you have water flowing. So here it's gonna spinning around. If you take vector calculus, it means there is a curl, there is a rotation happening. So hydrodynamics is gonna be very important. Okay, so just an introduction. Are you with me? So doing vectors, it's cute, but it's a pen blank. So instead, we're gonna use streamlines. So that means where the lines here are packed, it means the vectors are larger, so it's going to move faster, right? When the density is smaller, it's going to move slower. Is that clear? Okay, so then we can see the force of gravity 2 ways. We can say there is a force at a distance, that's what Newton say, F equals mg, okay, force equals mg, or we can look at it a different way. And vector fields were introduced by Michael Faraday in when he was looking at electromagnetic fields. So he introduced those field of forces. So video, picture, field lines. I don't know. Field lines. Okay. Here you have another example of a vector field. That will be the magnetic field of the Earth, for example. So you know the Earth has a magnetic field to protect us against those dangerous radiation coming from space that are charged, right? So it goes out of the north into the south. This is called a magnetic field. So when it's packed here, that means the field is going to be very strong. As you move away, you see the lines are apart, so it will be weaker. So this is an example of a vector field. And instead of using vectors, arrows, they use streamlines. And there is a direction. Magnetic field goes out of the north into the south. So that's just an example. So to go back to the Earth, so if you have the Earth here, it's going to generate an aura. We call that the gravitational field that goes into the Earth. Goes into the Earth, right? So it should be uniform all around. It only depends on the distance r. So if you place a mass here, okay, it's gonna feel, it's gonna know, oh, I am in a field here. I have to react to that. So it's gonna respond with an attracting force here. So the force of gravity, which is equals to the mass times the field. The gravitational field in magnitude, it makes sense that it depends on the source, which is the Earth, and how far you are from the source, so the distance squared. So the gravitational field obeys a inverse square law. So whether you have a mass here or not, the field is here nevertheless. It's just that if you happen to have a mass, that could be you, okay? It could be you here. So you're going to be attracted to the Earth, okay? F equals mg, or it could be the moon, okay? So on Earth, g is just 9.8 meter per second square. As you move away, it goes to 0 at infinity. So that's just a review. Any question? Remember that? Now, you can look at this equation a different way. If you take that equation here, so that will be the force due to gravity, okay, equals the mass times the field. Now I can write it this way. The field equals the force divided by the mass. So that will be Newton per kilogram. So you can think of the field as the force per unit mass. Okay, that's going to be important when we get to the electric field. Okay, so that means it will be, if you have 1 kilogram, okay, that force here will just be G. Okay, so you can think of G, the gravitational field, the force applied to 1 kilogram of force. Okay? Okay. Newton per kilogram. Okay, by the way, for those who take who gonna take vector calculus, you see it's like a vacuum cleaner, right? Sucking. That means it's a source. This is called the source in vector calculus. It's like the flow. Something is flowing in. Okay? So it turns out that if you take a negative charge, okay, if you take a negative charge, negative charge, it will behave exactly the same way. If you take a negative charge, it will create an aura. We call that aura an electric field. A negative charge is like a sink. It's sinking in. It's sucking in. So it's always attractive if you have a positive charge there. Now, a positive charge will also create an aura, but it will be the opposite. So in vector calculus, it's called a source. Okay, so I can show you that. Once you know, physics is about understanding the concept. Once you understand the concept, at least for physics 2, calculus based, once you understand the concepts, it's just stupid math. It's just the concept. Once you understand the concept, you're good. Okay, so I take a source. No, this is a sink. So that will be behave like so I take a negative charge, can make it stronger here. And you see, it's gonna generate like an aura, which is called the electric field. If you place a very small charge and the charge is positive, do you think it's gonna be pushed away or attracted? Attracted, right? It's positive, positive and negative attract each other. Because this is called a test charge because it has its own electric field, but because it's so small, it's not going to disturb this one. Okay, so as you move closer to it, it's going to be very strong. As you move away, it's going to be very small. Okay, so a negative charge is a sink. Now, if you take a positive charge, that's going to be a source. So negative charge behave like the earth. Positive charge is like a hair dryer. It's blowing, it's blowing. It's an aura. So now you see positive and positive repel, and you can each point in space. In each point in space, I can define the vector electric field, and you can think of the electric field as the electric force per unit charge. Okay, so it's the electric force per unit charge. So it's like the Earth. So now we can have, instead of having this, let's say we take a negative charge, so have a negative charge here, like an electron or a balloon, like charged negatively. Maybe not a balloon, a Van Graaff generator. Okay, so if you have a Van Graaff generator like this, electron will be all over. And so then you have the electric field all around, which is radial. Okay, it's a radial configuration. So if I place a little charge here, right? So that will be the electric field. So that will be the notation. And if I have a little charge here, and this is positive, it's going to be attracted here. That will be the electric force. Okay, so the electric force, instead of being mg, it's going to be qe. mg qe. Okay, now you can think of the electric force. The electric field is the force per unit charge. So the unit is Newton per Coulomb. So help me here. The gravitational field, remember the gravitational field in magnitude, it was that constant, ridiculously small, the mass of the Earth and the distance squared. So the electric field will be what? What do we have instead of G? Instead of G. So that's the gravitational constant. Instead of G, we have K. The electric constant, right? 9 times 10 to the 9 to say, be careful. electric force is much larger. What's the source? Before we had the mass of the Earth, so now we're going to have the charge, right? And will be distance square. Okay, so that will be the magnitude of the electric field, except the configuration is radial. So it's for negative charge, it's a sink. For positive charge, it's a source. That means if you are taking calculus, vector calculus, that means you can compute the divergence of E. Okay, it could be negative or it could be positive. Negative for a negative charge, positive for a positive charge. So either it's going in or it's going out. Are you with me? Yes? It's not hard, right? If you are a lot of applications. So for example, sharks, they have a sensory system here with a little charges. I don't know what kind of charges it is, but they can sense electric field, but very, very weak electric field produced by very small fishes, for example, because they are blind. I mean, like me, partially blind. Okay, so electric field, you have the magnitude. If it's positive, it's going out. If it's negative, it's going in. Agree? Okay, the other thing that you have to understand is that if you have an electric field, then you have to memorize because it's a typical conceptual question. Let's say you have an electric field. Electric field, imagine, is like something blowing. Okay? It's blowing. If you have a positive charge, then it will go with the wind. So it will move in this direction. F equals QE. And you see that the electric force is proportional to the electric field. So if the electric field is in this direction, the force will be in this direction. Okay? Just memorize for now. So a positive charge inside an electric field will feel the wind and wants to go with the flow because it doesn't like confrontation. And then a negative charge has a critical mind, right? Like me, you tell me to go to the right, I will go to the left. I will do exactly the opposite. So a negative charge, right, will do the opposite. So a negative charge will go always against the electric field. Okay, so like it's when you are told something like do this, 80% of people will do it, and then you have those crazy people, including me, who will not do it, will not comply. I try not to comply. So think of that negative, they have a negative mind, they go against. Positive, they go with the flow. Okay? Yes. No, this? No. This is a tangent. I don't care. This is my last semester, so I can take as many tangent as I. You can complain. I don't. No, this is no. It has a name. It's a principle that when they say do this, 80% of people will comply and 20% of people will go against it. Right? Why are you saying that I have to go this way? It's suspicious. I'm gonna try the other way, right? So it's a fact. Like it's statistically it's correct. Okay. But I should not take that many tangents. Okay. So we can map electric field using oil and seeds, little seeds here. So what's happening here, for example, you charge that, so that will be an electrode. Let's say it's positively charged. And this is oil, and you have little seed. And this seed will get polarized. Okay, they cannot move because they are not charged, they are insulators, but they get polarized. So I will show you a demo, but you see, let's say this is plus here. Let's say this is plus. So again, plus, it's it's going to be outward, right? It's a source. So that will be the electric field here. So what's going to happen in those seeds here? They are insulator, but I'm going to magnify one here. Okay, it gets polarized. That means the electron will go toward here, and because they have a negative spirit, they want to go against the electric field, and this one wants to go toward the electric field. So they will rotate. There will be a torque applied. So if the seed was this way, you see, it's going to rotate. Okay, it's called the torque, and then the minus and the plus, and it's going to align with the electric field. So that's the way we have to map the electric field. And again, it's called polarization. Yes.
Um, on the last example you showed with the positive and negative charge, positive going with the current and negative going against it, is the force equation for the negative one the same? The magnitude is different?
Yes. No, the magnitude is the same. F equals QE if they have the same charge. The direction is not the same. So it's just the magnitude, okay? Is that clear? So this is very important because we're going to, that will be called a dipole because you have a minus and a plus, and there will be a torque applied to the dipole such as it's going to align with the electric field. Okay, so let's look at if you have a demo. So let's look at this demo. So in that case, it's a different geometry. So one is positive, so this is connected to the plus of a battery. That will be connected to a minus of the battery, so power supply. Let's say this is plus, this is minus, right? And I will find a better example, but let's say this is plus, and let's say this is minus, because this is plus of the power supply, this is minus of the power supply. So electric field always goes from plus to minus, always, because it's always out of the plus into the minus. So that will be your electric field here, out of the plus into the minus, and you can see the little seed here. Usually they use castor oil because it's thick. Can you see those? They are aligned to each other. Interestingly, do you see any pattern here inside? Nothing. That means there is no electric field inside. This is called a Faraday cage. If you are inside a conductor, there is no electric field inside. Okay? We'll talk about that, but it's just an introduction. So let's see.
With the little grains of semolina, quite a positive and negative charge.
What's a British accent?
Exciting time.
Exciting time, yes. Okay, let's see if I have here. So now that will be the configuration of a capacitor, okay? So that will be positive, that will be negative. Electric field goes from plus to minus. So let's see the configuration. So there is nothing. And then he's going to apply 5,000 volts, something like this. Okay, connect to the power supply. So one is plus, the other is the ground. Okay, I don't know how many voltage. It has to be a big voltage. What does it say? Oh yeah, thank you. 4,000 volt, thank you. 4,000 volt. And now you should start to see those lines here because those little seeds get polarized in between. There is nothing, so no electric field here, no electric field here. electric field will go from plus to minus. Is that clear? And that's how a capacitor works. Here, see, plus, minus. Electric field goes from plus to minus, so it's being pushed by the plus, sucked in by the minus. And you see those lines are uniformly distributed, which means it's uniform. The electric field is uniform, it's constant, right? Bless you.
I can prove that.
And screaming.
Sure, two configurations in the system of the diamond and CO2 charges which are equal.
So what you're going to see here is the configuration for a dipole. So this is plus, and that will be minus. So this is spherical, and you have all the seed here in the oil. See? You apply the power supply. So what you visualize is the electric field that goes from plus to minus. This is called a dipole. Out of the plus into the minus. Dipole, very important in chemistry.
Each one of the charges, nice arcs in between. We see it easily. So
So, okay, you can find, you can go. So, for example, here, that's a way to visualize the electric field. You see, let's say this is negative. Negative goes all through the body. She is isolated from the ground, so she steps on something that will isolate her from the ground. So, negative will move all the way, and that will be the electric field. You are visualizing the electric field, right? You can do that with a plasma globe. So this is amazing because it's very cheap. I mean, relatively cheap. I have to buy my demo because it's too much paperwork to get a demo from the department. That's another story. But it's a plasma globe, right? It's amazing technology because they use Tesla coil inside. So inside you have a coil and inductor, and you have a capacitor. With the magic of physics and electronics, you go from. Do you know what is the voltage from here? From your USB? Not 12 volt, 5 volt. It's 5 volt, right? So if you take a USB, you cut it, you measure the voltage is 5 volts. You go from 5 volt to like 100 volt. You boost the voltage with a Tesla coil and a capacitor. So Tesla was a genius. And you can look it up, the Tesla coil, how it works. It's a genius idea. So anyway, just with my computer, so 5 volt boost to, I don't know what's the voltage. Can you see the lines here? So this what you are seeing here, visualizing, is the electric field. The electric field goes, let's say it's positively charged, so high voltage to the outside, because outside will be the ground, and it's radial. So inside you have some kind of gas, plasma, and a gas that gets ionized because of the very strong electric field. It make it through, right? So if I touch it, it's very happy now because it can go through my body into the ground, but it's so small that I'm not feeling anything. But you can see here. Isn't that amazing? So you see the electric field is not something, it's real. You can visualize it. And I highly recommend that you ask ChatGPT how it works because it's amazing. Yes.
So they can shock it.
I don't know if it because it's a good question. So it's complicated. It's because the glass here will behave like an insulator, so dielectrics, and it make the electric field weaker. So I don't know if I will have to get a very high voltage. So I'm not sure. But otherwise, no. Even the big one doesn't shock you. Yes.
Also, car batteries are 12 volts, correct?
Yes.
Why isn't there so like how is it possible? I guess it's just ignite like the fuel, never mind. But I was gonna ask like why are they so big if it's just 12 volts and like
Okay. So for the energy, you need two things. You have the voltage and the current. So even though the voltage is small, the current will be large. So you need a lot of chemical reaction to have large current. So it's a good question. It's the difference between the AAA and the D battery. They have the same voltage, but the D battery burp out more current. So that will be more energy. So it's not so much the voltage that kills, it's the current, right? So in principle, if you touch the plus and the minus of the car battery, you should be okay. But don't do it. Okay, so here, electric field, you can think of that as the electric force per unit charge. That's how we represent the electric field. And you see, you double the charge, you're going to double the electric field lines in our protocol. Okay, so that means that the electric field will be stronger. Okay, it's more packed here. It goes as an inverse square law. Electric field lines always start from plus, goes to minus, and they cannot intersect. Okay, so again, plus is a source, like think of positive mind, the source of good vibe, so out. So it's a source, plus is a source, minus is a sink, F equals QE. That will be the equation for the electric field. Okay, so which one is false? B, right? B. Negative mind go against. Right? So let's do just one to apply. So don't worry about what it says. Just find the electric field of a charge equals to 15 microcoulomb. They make things more complicated than it is really. So you want to find the electric field at that distance here from that source. Positive mind, positive vibe, everything goes with the flow. It's a source. So if you have a positive charge here, it will be pushed away. So anyway, find the electric field from that charge here. Just for the computation. Just apply the equation. Okay, so the electric field in magnitude, we're gonna focus. So it's the electric constant. The source is Q, the distance R square. Okay, so it will be 9 times 10 to the 9. The source 15 times 10 to the negative 6. And the distance square. Okay? So with your TI, you do that in one shot. How do you get? One shot.
50.62.
50.62? You sure? Let's see. 3 times 10 to the 9 So that way you see how I do it, right? You close the parenthesis, open the parenthesis, and then 15 base 10 is second comma. That's the base 10. -6, okay? Enter. Divide by open the parenthesis, 0.2 square. Yeah, this 1, 2, 3, 4, 5, 6. Yeah?
Yeah.
Okay, so 3.4 times 10 to the 6 Newton per Coulomb. That means that here, if you have 1 Coulomb of charge, which is positive, okay, it will experience this force here. Newton per Coulomb. Coulomb is the unit for charge. That's a lot because 1 Coulomb is a lot. So 1 Coulomb, like Van Graaf, will be in nano Coulomb. So 1 Coulomb is just for the sake of computation. And so because usually the charge is much smaller, the charge in that case, they say, let's say you have a charge of 15 microcoulomb now. So let's say now here at that place here, I'm going to put instead 15 microcoulomb. Okay, so F equals QE. So the electric force will be Q times this. Do you agree? You can think of that. This is for 1 Coulomb. So if you have 15 microcoulomb, you just multiply. F equals QE. Okay, like F equals mg. Yes?
Microcoulombs, wouldn't they feel more force?
So so if you have 1 Coulomb, it will be more force, right? But 1 Coulomb is just for you to compute the electric field. Usually the charges are very small. Right? Van Graaf generator is like a nano Coulomb. It's very small. 1 Coulomb kills you. I mean, in current. So that goes bye-bye. So that's going to be, well, 51 Newton?
Yeah.
Okay. Thank you. Okay. So the electric field is the charge per unit Coulomb. So electric field, you see you have different value here. So here is the interesting thing. The electric breakdown in air. What does it mean? It means that, let's say you have a Van Graaf generator. So if you have a Van Graaf generator, okay, you're going to have an electric field when it's charged. Okay. So this is your Van Graaf generator. Let's say, just to understand, here and then here. No, how can I do that? I don't know how to do it. Okay. Okay, let's say you have a Van Graaf generator here, and then let's say this is minus. Minus will go all the way. So now it's a source. So that means you're going to have an electric field here. Okay. It's going to be not exactly like this, because here, if there is minus here, you're going to have plus. So, but let's say it's like this. So all those air molecules here, they get polarized, right? So you have a plus here, minus there. That will be the electric field. If the electric field gets larger than 3 million Newton per Coulomb, guess what's going to happen? A discharge. It will discharge. The electric field is so strong that the electron will jump. You get ionization. The air will get ionized and it will make a discharge. So if the electric field is larger than 3 times 10 to the 6, you get a discharge. How can you get a discharge? For example, if you come here with your big nose close to it, right? So what's going to happen? Here it's going to be all plus. Going to be plus, 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 but especially on the pointy thing here, right? Or it could be your finger, for example. So all those electric fields here will go from, sorry, see, I did a mistake. What is the mistake that I've done? Huh? The electric field for a negative charge should go toward, okay, should go toward. Because it's a sink. So anyway, so you're going to have a very strong electric field here between you and the Van Graaff. So electrons get very excited because they see they can combine with the plus. The electric field will increase in magnitude and you have a discharge. The discharge, and then the electron can go to the ground. Okay, so if the electric field get very strong, then you have a discharge. You have a spark. Okay, yes. Lightning, yes, yes. Exactly. So I don't know if I can show you that. You will get lightning, you get shock, but you won't die. That's what you get. So this is a pencil. Pencil, you know, it's carbon. Carbon is a conductor. So the electric field is so strong between your finger and the Van Graaff here that you have a discharge and you have lightning because it gets ionized. Boom. Boom. Isn't that fun? So thunder, that's how thunder works, right? So if you have the ground is a reservoir for charges. So if you have a cloud here, and let's say you have rubbing, so that becomes plus here. Somewhere it's going to be minus. So all the minus will go here. And an electric field goes between what and what? Plus or minus? Minus and plus. Positive, good vibe, right? Okay, from plus to minus. And if it goes over 3 million Newton per Coulomb, zing, you have lightning. Discharge. It's called discharge. Corona discharge also happens in hot lines. Okay, superposition principle means that electric field is a vector. So if you have two sources, so this is a source here, this is a source here, at that point, you're going to find the electric field produced by this one, the electric field produced by that one, and then you combine. Because electric field is a vector, you need to add vectors. So if it's far away, everything happens, it's just one charge. If the distance is large enough, it's just a positive Q and a positive Q. So you need to add vectors. Okay, let's try to do this one. So you can guess. You can guess the answer. Oh, but let's do the computation. So you have 4 times the charge and then this one. So this one is 4, this one is 16. And you want to find the point where the electric field equals 0. So typical question for a test, okay? So let's try to simulate. So I take 4 times the charge here. So 1, 2, 3, 4. Okay, so 4 times, and here only 1. I'm going to put it here. So you see this, you have 2 electric field, one from this one and one from that one. This is called a distribution of charges. Now, if I take 1 Coulomb, let's say this is 1 Coulomb, it's going to be pushed here. Here it's going to be pushed, but there is a place in between where the electric field will go to 0. Do you see? It's like wind colliding with each other. You have wind from this one, you have wind from that one. At that point here, it's going to be 0. And you can visually see that the distance here is 1, 2, 3, 4. The distance here is 1, 2. So you have a ratio of 2 to 1. So you could have guessed without doing the math, but we're going to do the math. Do you understand the question? So find that distance here, where the electric field equals 0. So you have to think of electric field like wind. Okay? They interact with each other. Okay, so you want to find that distance where the electric field from this one will be cancelled out by the electric field from that one. Okay, do it, because it's just math. It's good for engineering stuff. Do it. Help each other, talk to each other. So you can think of electric field equals 0. The net force equals 0. So we deal with electric field. We're going to pretend that you have 1 coulomb of charge here. And this is positive. So this coulomb of charge is going to be pushed away. And this is positive. So it's going to be pushed away. So the net force for 1 coulomb of charge is E1 plus E2. And we want that to be 0, which means that in magnitude E1 equals E2. Agree? This is 4 times. This is 16. And this is just 1. And you place 1 coulomb of charge. So again, the electric field is the force per coulomb. So the force for 1 coulomb. Okay? So you want to find E1 equals E2. Yes? And you use Coulomb's law. So the force on 1 coulomb from Q1 is just the constant. The source is 16. And then micro coulomb. And then the distance is g squared times 1 if you want. Okay, the electric field is the force for 1 coulomb equals K. The source here is 4 coulomb, and that's 1 over 3 minus g squared. Okay, go. Okay, we're gonna play the bye-bye. Bye-bye. Okay, we multiply both sides. So 16 times 3 minus t squared equals 4t squared. You square on both sides. So 4 times 3 minus d equals 2d. You distribute. So it will be 12 minus 4d equals 2d. So 12 equals 6d. So d equals 2. Agree? It's just math. Don't complain to your math teacher, not me. Okay? By the way, you can do it here. You see? 1, 2, 3, 4. 1, 2. that distance has to be twice as large because it has 4 times the charge. Any question?
Can you explain why you made at that specific point? Why was it 1 Coulomb?
No, because by definition, the electric field is the force on 1 Coulomb. So the electric force is K, Q, the first charge times the second charge, okay, over the distance square. So that's the electric force. No, by definition, the electric field is the force produced by Q. So let's say that will be Q, for example, for 1 Coulomb. So that means if you are in space, okay, so let's see, you want to find, you have a source here, that will be the electric field, and you want to find the electric field at point P. You imagine that you have 1 Coulomb of charge. This is positive, so it will be repelled. So the electric force will be charge number 1, charge number 2, divided by the distance square. So the electric field, one way to look at it is the force per 1 Coulomb. Likewise, F equals mg, the gravitational field, you can think of that as the gravitational force divided by the mass. Force per unit mass, force per unit Coulomb, so for 1 Coulomb. Okay, this is called the test charge. It's like you are testing, but you are not interfering with the source. Yeah. Because, okay, that's your 1 Coulomb of charge, right? So if you close to this one, so this one is 4, this one is 1. So you see, it's being pushed away by that one. And close to it is also being pushed away. But in between, it's going to be pushed away by this one and pushed away by that one. So it's going to cancel out. Okay, so it's like someone is pulling me in this direction, someone is pulling me in that direction, so I'm going to not move. Okay, so at that point only. If I move along, it's going to be different. Is that clear? Now, if you have the same charge, if I have the same charge, I have 1 Coulomb and 1 Coulomb, it's the place will be just at the center, right? The place will be just at the center here. 1, 2, 3, 1, 2, 3, because the charges are the same. Here? Okay. Okay, so this is just a conceptual question. All you have to do is to draw the net electric force, electric field. It's using the superposition principle. So we want to find the electric field at the center. So we're going to pretend that you have a 1 Coulomb of charge here. And let's look what's going to happen to it. And then you're going to compare to this situation here. So you have a different distribution of charges and you want to draw the net electric field. They started, but they didn't finish. Okay, so why don't you draw? So you have 1 Coulomb of charge here. Draw the forces acting on that 1 Coulomb and try to draw the net force, okay, using adding vectors. So the parallelogram method, and you do the same thing here. And just with your guts, you can find in which situation the electric field will be the strongest. Okay, so do it. So when you want to find an electric field, imagine you have 1 Coulomb. Positive. So it's going to be attracted. Do you agree? And then here, from this one, is it going to be attracted or repel? plus and plus, they repel, right? So it's going to be repel. The magnitude is the same. So this magnitude and this magnitude are the same. Okay, because it depends, the distance is the same, the charges are the same. And then from that one, it's going to be what? Positive and positive repel. Okay, so that's going to go this way. And then from that one, repel. Okay, so you see this one and that one, they're going to kill each other out, right? So you add those two vectors, so the net electric fields will be this gonna be twice as big, right? Gonna be something like this. This one plus that one. Yes? Okay, and then you do the same thing here. So they already started. So 1 Coulomb attracted, and then it's gonna be pushed. And then it's gonna be pushed. So it's gonna be twice as big. Right? So you add this one plus that one. So what you should see is that this one will be larger than that one, just with geometry. Okay, you can do that on your own. This is not physics, it's just geometry. Triangles and parallelogram. Okay, ideally, if you want to go in engineering, you should have graph paper with little square. I mean, if you have a tablet, you can have those little graph paper, and you can trace and convince yourself. It's a good exercise. Okay, and then so make sure to do your textbook. Then it becomes heavy in math, but so you have to study. So anyway,